So other common modes of behavior are generated by interactions between the fundamental patterns. These include, for instance, overshoot and collapse, and also oscillations that depend one stock over the other one. So the first example that we are going to discuss is overshoot and collapse. Overshoot and collapse occurs when one stock depends on the other one, but the other one has a limited, the resource is limited, okay? There are many examples where this happens, and this is actually somehow similar to the logistic growth, where we have a carrying capacity, but in this case, this is we are tracking also the second stock. So before we were talking about food, space, etc., but we were not discussing how those stocks were behaved. And in this case, we have a truly equation that involves exactly the second resource, and that it is interacting with the first one. So how can we know, by having only the equations, how can we know that these stocks are interrelated? Well, this is very clear by seeing that the first stock is also involved on the equation of the second stock, and also in the first equation of the first stock, the second stock is involved, right? So R is also included in this equation, and P is included in this equation, okay? As you can see, if we want to guess how many flows do we have here, we can have one flow that is a bird, and then we have the dead, and we can have dead and another flow. We could have also an additional flow here, or we can have a combination involving all these together, right? So this is the dead, and it has all these components, right? It has P on this part of this flow. It has P, it has R, and it has R0, okay? I hope that now you can start understanding how, if I give you the equation, how are you going to construct the stock and flow diagram? Okay, the second stock is a little bit easier to understand because it only has one flow, and it is one negative flow. So this means that this stock and flow diagram is incorrect, because the direction of this arrow should be on the other side. Okay. So I'm going to correct this on the slide. So the consumption of the arrow should be pointing to the other side, so we have a negative value. Okay. So if the resources are renewable and can regenerate, then the system will collapse toward non-zero equilibrium. However, if resources are non-renewable, then the system will collapse towards zero. So in the example on the problem set, we had the problem number 5 was the people in the island, and it had a similar stock and flow diagram, but differing from this one, it had also something increasing the resource, the second stock, right? Not only one pointing out, which it should be here, the consumption, but it had also something feeding the system. Okay, so this is what this statement refers to. So we can it's towards non-zero equilibrium, or it can be completely collapsed towards zero. Clearly, we can see that in this case, even if it's on the other direction, we have a causal loop diagram that can be generated with feedback loops. So this is how the feedback loop, the causal loop diagram will look like of the overshoot and collapse. So the first part is the same as we saw on the logistic growth, but then we also have a third loop, a third negative loop or dampening loop, okay? And this is how our figure will look like. This is the typical behavior of the overshoot and collapse, where R, the resources, are starting getting to be depleted, while the population will have a point where it reaches its maximum value, and then it starts decreasing, right? So the equilibrium is an asymptotic equilibrium, where P equals 0 and R it will eventually reach a 0 value, or it will be smaller than 1, referring to the birth, because B is birth, so it will be smaller than 1. So now we're going to discuss our second behavior interacting two stocks. This is the oscillation behavior. The main feature of an oscillating system is the presence of a strong counteracting feedback loop that forces the system to oscillate around an equilibrium set of conditions. Some examples of this type of behaviors are encountered in weather, like rainfall patterns throughout a certain period of time, like also drought and rainfall, big rainfall periods over 4 period of years or 5-year period, etc. We also have this behavior on ocean tides, on predator-prey systems, and systems with consumers and renewable resources. So systems that have a renewable resource that can recover and that can allow to increase the second stock. So the basic characteristics of predator-prey systems are the system contains at least 2 independent reservoirs or stocks. When one species becomes the full resource of the other, but this is only for population. It can be also this behavior depending on one stock over the other stock that not necessarily is a food. The third characteristic is that the resource is not unlimited, and being represented by the exploited prey population. So without predation, the prey behaves like a single species population reaching its carrying capacity. Without prey, the predator cannot survive, assuming that no alternative food source is available. The consumer and resource reservoirs have equilibrium values around which they oscillate. The further one reservoir is from its equilibrium value, the more influence the other reservoir exerts to pull it back toward the equilibrium. And now we're going to explain how it behaves. These are the equations, not organized based on the as differential equations. So as we have said before, how the time steps are calculated, right? But these are the equations, and these equations lead to this stock and flow diagram. Again, we have R, that is the component of the second stock within the equation of the first stock, and we have P as also included in the second equation of the second stock, okay? And G, D, W, and C are rate constants. So the steady state condition, or the equilibrium, can be calculated by by canceling the accumulation or differential component to equal to 0, and then solving for P and solving for R, right? And then, so P will be equal to W divided by C, and R will be equal to D divided by G. So this is how, since we know that we say that all these values were rate constants, then they won't be constructed as equations. They just have a specific value. Okay. And this is how oscillation will look like. Okay. And the steady state that I mentioned to you that it can be estimated will only show, it won't show you, of course, the oscillation, but we will show you the middle point where the system oscillates. Okay, the range where the system oscillates. So with these equations, we can have, we need an initial value for the both of the stocks for the system to start to have a valid solution, right? And the numerical solution that was also described at the beginning of the oscillation behavior slides was this one, right? So this one can be, this is the breakdown of this equation, and this is the breakdown of this equation. All right. Later on, you will see that we're talking here about numerical solution, and this is the simplest method, which is the Euler method. But later on, we will see that if these rate constants are very different from one over the other one, Euler method won't be the most ideal one for solving these type of behaviors. So when we have different stocks that have rates that are at different scales, we may use other type of numerical methods. So on our problem set for this lecture, you will have to change the method in the Stella, in the model specs. So solving the equation of the equations of oscillation will lead to the asymptotic periodic solution that are given here. All right. Also, it's worth mentioning that oscillations are also caused by goal-seeking behavior on control systems. However, delays mean that the state of the system overshoots and undershoots the goal. The time delays cause correction actions to continue after the state of the system has reached the goal, leading the system to adjust too much. So yes, on control systems we can have oscillation behaviors. I put this picture because also oscillations, as I mentioned before, can occur due to rainfall or to a specific addition of flow patterns that can lead to oscillation behaviors. Also, in general, for example, climate change has been seen as having oscillation patterns that are yearly oscillation, but also other oscillations are in a bigger scale, right? Like glaciations, for instance.